Hello everyone. Let us continue our discussion on reinforced concrete design. This is the 9th week, and in this week we are in the first lecture. In the previous lectures we have covered reinforced concrete design based on IS 456, and we designed the component of a structure, for example slab, beam, column, footing. Then beyond that, in this series of lectures we wish to also go through the design of some special structures. That also we have covered in the previous two lectures, if you recall, deep beam and flat slabs, right? Now let us consider a different type of structure that very often we encounter, and that is underground water tank. Now these underground water tanks, they are basically a storage tank for water, and we use them as a reservoir. So this is the ground level, and a concrete tank is made with a cover below the ground. Now the main purpose is storage. Okay. Now as you can see, surrounding this water tank, actually there are soils. You can also see that in this picture. Now the time we construct this water tank, first the trench is dug out and the soil is removed. Then the construction is made, and after that soil is filled up, right? Now if you see this water tank, it has walls on the side made of concrete, and at the bottom there is a base. So when we design this structure, obviously we have to consider the critical load combinations, and for that you can easily identify. So the soil surrounding this water tank will apply a pressure, and if there is liquid inside the tank, that liquid will also apply a pressure. So the critical loading conditions can actually vary. One situation is that the tank is empty and then only the soil pressure will act. On the other hand, we can have both soil pressure as well as the water pressure inside the tank. Beyond that, there can be a situation during the construction when the surrounding soil in the place of tank, this soil is not there. It is filled after the construction is made, right? And during that construction also, to check the leakage, water is filled up. So in that situation, there is no soil surrounding this tank, only water pressure is acting. So these are the different load combinations that we very often encounter when we design a storage tank. And as we progress, we'll see, we will consider the soil pressures and the pressure of the water, and then accordingly we will design. Okay. Now, before we go into the details of this design, let us first go through the codal provision. So this is the code for liquid storage, right? Now, we will follow some of the guidelines of this codal provision as we progress in this design. Now, the first thing we have to consider is the lateral pressure due to the soil. As you can see here, there is no soil here, and later on the soil is filled, and the moment it is filled, the wall of the storage tank experiences a soil pressure. Now for that, we use Rankine's theory. If the density of the soil is gamma, then the lateral pressure, the intensity of that pressure at a depth h meter, can be expressed by this equation. So P, which is the soil pressure, is gamma times h times 1 minus sine 6 degree divided by 1 plus sine 6 degree. Now, in this theory, we assume the angle of repose is about 6 degree, and hence you can see here. Okay. Now, once we remove the soil at the site. Then first a formwork is prepared and the concrete is poured for this construction of this wall at the 4 edges. If it is a rectangular tank, and for the time being, let us consider rectangular shape only. Before that, a soil is prepared at the bottom, and then a slab is cast that forms the base of the tank. Okay, so here is a soil bottom. On top of that, a slab is cast that forms the base, and then on the sides, the walls are constructed. Okay, so now after that, once the soil is filled, the soil pressure acting on the wall is also affected by the groundwater level, right? So if the groundwater level changes, then that affects the pressure. Now, when we design this type of tank, we consider the base having rigid joint here, as you can see. Now, when we have this type of construction where the slab base is actually monolithically cast and this side walls are there, then if we fill up with water, obviously the water will apply a pressure, and that will cause hoop stress over the walls. Now, at the top, there is a support from the roof. So this vertical wall, it acts like a cantilever. As you can see, the pressure distribution here. At the bottom, we have the bending moment, which is negative, is caused by the pressure, and its magnitude is pH square by 15. And the positive bending moment, as we go up here, it is pH square by 33.5, right? So we'll use these values of bending moment and we'll design the side walls made of concrete to withstand this bending moment, right? Okay, so let us see how we can design and detail this. Let us take an example. So in this example, what we have is a dividing wall in an underground water reservoir. And this wall needs to be designed. We have M30 grade of concrete and Fe415 grade of steel. And the geometric data is given. So height of the wall above the base is 5 meter. Maximum height of water above the reservoir floor is 4.5 meter. And the reaction at the support caused by the water pressure, which is triangular, obviously as we go deeper, water pressure will be more. So this is triangular in shape, right? So this triangular water pressure is taken as 1/4 of the total triangular load. So for the base, the fixing moment is given by this expression. So in this expression, P is the intensity of water pressure, small h, height of the reservoir, that is the height of the water inside the reservoir, and capital H is the total height of the wall that we are going to design. And then Y is the freeboard. So we are going to use this expression for the moment against which we will design this. Okay. So for this case, let us first identify the most critical loading condition. And it occurs when the reservoir contains water only on one side of the dividing wall. Because on the either side, if you have water, that will counterbalance depending upon the height of water on the either side. So for the worst case, let us consider one side is having water, other side is empty, so that we have the full water pressure is acting. And we have this geometric data already given. So for that, we can evaluate the pressure at the bottom of the wall which is 9.81 times 4.5, and this is 44.145 kilonewton per meter square. So at this location, we now have the pressure. The next is we have to find out the fixing moment at the base per meter length of the wall, and for that we already described this expression. So in this expression, if we put the respective values, the pressure we have already figured out, that is 44.145. Small h, it is 4.5, capital H is 5, and y, that is the freeboard, is 0.5. So from this we get the moment at the bottom is 66.524 kilonewton meter. Now you can see this diagram of the dividing wall. Now on the right hand side of the wall is where the water pressure is acting, and at the base we have this moment. So the triangular load due to water pressure we can calculate, and if that is P, which is actually half the pressure at the base times height, which is 99.326 kilonewton. So the reaction at the top, it is P by 4 and it is 24.8316 kilonewton. Right? Okay. Now from the top, here is the pressure diagram. So from the top, if we find out the bending moment at a location X, the mx is given by this expression. Now obviously we have to find out where we have the maximum bending moment, and for that we differentiate mx with respect to x, and if we solve at x equal to 2.3, we have the maximum bending moment. So we can also find out the value of that maximum bending moment at x equal to 2.3, and it is 39.63 kilonewton meter. So at the base we have the moment 66.524 kilonewton meter, and somewhere at the middle we have mx, which is 39.63 kilonewton meter. Out of that, the maximum one is 66.524 kilonewton meter. So we'll use that value to design the wall. Right? Okay. So let us see how we can design. So first we have M30 concrete, and that is the minimum grade as per the code we refer. So sigma C is 10 Newton per millimeter square, and sigma T is 130 Newton per millimeter square, because we have a grade of steel which is Fe415. And you can see the table here, table 4 of this code, that tells us the permissible values of sigma T, which is 130. Then we can estimate the modular ratio, which is 13 in our case, and small k, which is 0.67. If you recall, we discussed at the very beginning of our reinforced concrete design course, and the Q, which is 3.323. So the moment of resistance is basically Q times B d square. B is 1 meter, so this is 1000 times d square, and we have to equate that with the applied moment, which is 66.524 kilonewton meter. Now from this equation we can find out what is the effective depth of the section that we need, which is 141.4 millimeter. Then we can design with the effective cover of 40 millimeter. So the total depth is 182 millimeter. So we can provide a depth of 190 millimeter, which is sufficient, right? Next, we have to find out the steel requirement against a applied bending moment of 66.524 kilonewton meter. So AS is equal to M by sigma T times JD. So we know all these parameters, so we can find out AS, which is 5092 millimeter square. So let us try with 24 millimeter bars, and for that we can find out the spacing, which is 89 millimeter. So let us provide 24 diameter bar at a spacing of 80 millimeters center to center. Because the either side of the wall may be subjected to water pressure depending upon the situation, so we provide the same reinforcement on either side on both the faces, right? So if we have, this is the wall within the reservoir, and if we have, this is the case when we have water on both sides, or we can have water on either side, and for that we have already designed, and the situation may reverse, and that's the reason we provide the same reinforcement on either side. We will go through the detailing in a minute. So the first requirement of steel is met, which is here 25 millimeters diameter bar at the rate of 80 millimeter center to center. Now, if you recall, we have already figured out the maximum bending moment here over the wall, not at the base, and its value is 39.63 kilonewton meter, which is at a distance of 2.3 from the top. So from the top at 2.3, we have this maximum bending moment. Let us check what is the steel requirement for that, and it is here. So steel requirement for this demand is 3033 millimeter square. So if you use the same diameter bar, which is 24 millimeter, the spacing is 149 millimeter, which means at the bottom we have 24 phi bar at the rate 80 millimeter center to center. Then as we go towards the top, so after some region we can actually reduce because the requirement is less, so we can cartel some of the bars. I'll come to that in a minute. So for this demand, we have the provision of steel, which is 24 diameter bar at the rate of 150 center to center. Again, we can have water on either side, and that's why we have to provide the same steel on either side. Now, we have to also provide some distribution steel. So, if this is the wall, we have these main bars. So, we have to also provide distribution steels along the height. For that, the steel requirement is 0.3%, so it is 570 millimeter square. And if we provide 10 millimeter diameter bars, the spacing is 139 millimeter, so we can provide 130 millimeter. So we provide 10 millimeter diameter bar at the rate of 130 center to center, again on each face. So here you can see the detailing. So we have the main requirement of bar is 24 diameter at the rate 80 center to center based on the moment at the base here. Then as we go up, we can actually reduce the spacing, and we can increase the spacing and reduce the diameter number of bars, that is 24 diameter bar at the rate of 140 center to center we provide. Recall, from the top we have maximum bending moment at a distance 2.3 meter. So that means from the maximum bending moment at the base, when we come here, we have somewhere here a point of contraflexure. Beyond that, we have to provide development length, and after that we can reduce the number of bars. We can go for curtailment. So I leave a small exercise for you. From the base, you just find out where we have moment 0, that is the point of contraflexure, and from that point we have to provide development length LD, and beyond that we can actually curtail. How to find out that? Let me give you a clue. So this equation, if you put this equal to 0, you will actually get the location X from the top where bending moment is 0. Just find out that location and you can complete the detailing, the location where you can actually reduce the number of bar than what we design based on the requirement at the base. So it gives you a clear idea of how to design a wall of a water tank. So let us stop here. In the next class, we will see how we can design the side walls of a underground tank and what are the different requirements of steel for different sides and also at the base and at the top. That we'll cover in the next lecture. In the meantime, just go through this design procedures. Also, we have a new code. Just go through the codal provisions. If you have any doubt, please send us email and then we will clear your doubt. Thank you very much.